All right, so how is oxygen transported around the body? So let's look at that. So we know oxygen has to be transported through the blood. The blood contains red blood cells that contain proteins called hemoglobin that carries oxygen by and large. So in a red blood cell, that is where about 98% of oxygen is transported inside the red blood cell. About 2% floats free in the plasma. So most of it is in red blood cells on hemoglobin. So a red blood cell, so one red blood cell contains about 250 million hemoglobin. Hemoglobin molecules. And molecule. If the hemoglobin is saturated with oxygen, one hemoglobin holds 4 oxygens. So if the hemoglobin in a red blood cell is saturated, it can carry 1 billion oxygen molecules. That's a lot in one red blood cell. So hemoglobin. So let's review here. A hemoglobin is basically 4 proteins here, tertiary proteins that are linked together. Okay, and inside these proteins is this thing called the heme molecule. And the heme molecule has an important thing in it called iron. And iron loves oxygen. It is the iron on here that binds to the oxygen because it's really sticky towards it. It really, the oxygen just sticks to it like glue, like a magnet. Okay, so during gas exchange to the lungs, being on hemoglobin is the way to go for oxygen. The oxygen wants to ride the hemoglobin train to ride around. Oxygen does not really want to slide around free in the plasma. Okay, it doesn't really like that. So if we show, let me draw something here. So if we draw a little, same old thing, drawing an alveoli. Okay, and let's draw a big blood vessel here. Okay, and let's draw a big old red blood cell in here. And let's say we have taken a breath and our PO2 is 100 millimeters of mercury in the alveoli because we just took a breath. So oxygen is going to diffuse into the capillary because the capillary PO2 is going to be 40 millimeters per mercury. So as the oxygen diffuses in, it wants to get on a seat on the hemoglobin bus, the hemoglobin train, okay? And each hemoglobin, again, holds 4. So the oxygen is going to come in and it's going to hop on here to get on the hemoglobin. And when it does that, it's no longer oxygen, okay? It's oxyhemoglobin or whatever it is, okay? So when it becomes oxyhemoglobin, it's not oxygen anymore. So the PO2 in the plasma doesn't change. The oxygen is coming in, but the PO2 is still 40 because the oxygens are hopping on hemoglobin, and now we have oxyhemoglobin instead of oxygen. So that keeps happening. Oxygen continues to diffuse in, okay? And once these seats are full, which technically is about 98% full, so 98% is about saturated. Once that occurs, then the oxygen starts to go into the plasma, and this number starts to go up. And once it gets to 100 millimeters per mercury, no more oxygen can diffuse. Okay, so it diffuses until hemoglobin is saturated. Then it goes into the plasma until 2%, that's what's left, goes into, just floats around in the plasma. So from here, then we have transport over to tissues. But what makes the tissue, or what makes the oxygen diffuse into the tissue? So if we have our little red blood cell and we've got our hemoglobins full, so hemoglobin is full. And so when it is full, the PO2, a different color, the PO2 is 100. All right. At 98% saturation, it's basically full. Okay, then there's 2% left in the plasma, which makes the PO2 of the vessel 100 millimeters per mercury. Okay, so at the tissue, when it's time to unload, that pressure at the tissue, the PO2 in the tissue, again is the tissue's there. So PO2 is 40. That change, that 40, that's the lower, is almost a pull. And that change in, or that increase in partial pressure, the difference there allows for the oxygen to be less sticky to the hemoglobin, and it will move over. Okay, so it will diffuse in. Okay, as the difference increases, as the tissue absorbs the oxygen and it goes up to 100, then it gets less sticky. Okay, as that number equalizes, then it gets less sticky to the hemoglobin. So it has to do that. It's not like the blood, the oxygen goes over there, or the red blood cells over there by the tissue, and the tissue's like, oh, I need some oxygen. Oh, that tissue looks like it needs oxygen. I'll go ahead and just dump some over there. No. it has to be the difference in the partial pressure that attracts it. Okay, so that's really the main way that oxygen is transferred into the tissues, is through that gradient, that pressure gradient, or a partial pressure gradient. Okay. So in this picture that I have here, this is something called the oxygen hemoglobin dissociation curve. So this black part of the curve, the black part is normal. That's the normal curve of hemoglobin and oxygen bound to that. So you've got the percent saturation on this side and PO2 on this side. Okay, so up here where the PO2 is 100, the percent saturation is almost 100%. Right, we're at 98% right here. Okay, that's about as close as you're going to get. So you're almost 100% and you're at PO2 of 100. As the PO2 goes down, the percent saturation goes down. It gets less sticky. Okay, the oxygen starts to diffuse, starts to unhook to the hemoglobin to go to wherever it's going to go. Okay, so at PO2 of 80, not much of a difference. Here's 100, here's 80 right there. Well, it's still pretty close to 100%. At PO2 of 60, it's still 90% saturated. Okay, at PO2 of 40, it's a little less than 80. And then at PO2 of 20, boom, we're down below 40. Okay, so as that PO2 gets lower and lower, it starts to dissociate faster. Okay, so we have this, there are certain circumstances in the body that can speed this up or slow it down, that dissociation. So when you exercise, which means you're becoming more acidic because you're metabolizing and making more CO2, so the pH is going down, your temperature is going up because you're exercising, the CO2 is going up, okay? This BPG is going up, which don't worry about that. That is called the Bohr effect because it moves the curve to the right and makes the hemoglobin way less sticky. Okay, the opposite circumstances, so increase in pH, decrease temperature, blah, blah, makes the curve go to the left. It makes the oxygen more sticky. So when you exercise, you utilize more oxygen because you're making your hemoglobin less, there's less affinity for the hemoglobin or the oxygen to the hemoglobin. And so it's letting it go easier. Okay, so make sure you know this diagram, and obviously going to the right, that's going to make it less sticky. Going to the left, so this is less sticky, oxygen to hemoglobin, more sticky, oxygen to hemoglobin is going to the left. Okay, so make sure you understand that. The transport of oxygen is, it loads pretty easy. It loads easily to the hemoglobin. And again, there's 4 seats on the hemoglobin buses. And once they're full, 98%, and then the other 2% goes into the plasma. Okay. All right, so next we're going to talk about how carbon dioxide is transported.